Week 8, Problem 12. Within the green dashed circle shown in the figure below, the magnetic field changes with time according to that, where B is in Teslas, T is in seconds, and R is in centimeters. Okay. So they're all normal units except for the radius R. Okay. When T equals 2 seconds, calculate the magnitude of the force exerted on an electron located at point P1, which is at a distance of 6 centimeters from the center of the circular field region. Okay, so they don't talk about P2 at all here. Alright. So, first I see force, and I'm going to write up the equation that we use for force. Force equals EQ plus QV cross B. Alright, so my understanding of this question is pretty tenuous at best, but we're going to work through it and do our best as a team. So your first thought is, hey, P1, it's not moving, it's not in a it's not in the magnetic field, therefore this guy equals 0. Bam, done. And there's no, they don't even mention an electric field, therefore this guy has to be 0 too. Well, mostly. So you're right, P1 is outside the magnetic field, so the magnetic field does not, and P1's not moving. So it's stationary, right? Yeah. And it doesn't know if it says stationary, but I think that's kind of implied. So the idea here is the magnetic field does not really have an effect on P1. But magnetic fields don't even really exist. A magnetic field is just the result of a moving electric field, of moving charges. Charges have an electric field, charges move, therefore the electric field that's associated with the charge is moving. And that moving electric field is what causes magnetic field. So when they say they have a changing magnetic field, heck, probably wouldn't even they say they have a magnetic field at all. You're going to have an electric field. I think it's a changing magnetic field. We'll work through it. So I'm basically going to take the equations, throw them down on the board, and see what happens. So let's start with Lenz's law. Since they gave us an equation, and it's varying with time, so I'm going to throw down Lenz's law. By Lenz's law, I mean, I'm going to go with blue. I like blue. Oh, I'm already at blue. Bam. So we're going to say electromagnetic force, which is voltage. It is voltage. Negative d flux dt. Oh, go down over here. Equals negative dB dt times area plus d area dt times magnetic field. And we know this because flux is just B dot A. Okay? We know that the area of the circle is changing, not changing, so it's going to be 0. But we know that dB dt is actually something. So I'm going to do this real quick. Right over here. So dB dt equals 12t squared minus 2t. And then the plus 8 just doesn't matter at all. Alright, so this is the equation we have for dB dt. Maybe make it. Wait a second, can I just copy and paste? Heck yeah, I can. Copy. Paste. And let's say it's the right size. Okay. And we'll multiply this guy by the area, which in this case is going to be pi r squared. Big R. Perfect. Alright. Now we also know in life that the definition of voltage equals negative integral E dot, I'm going to say dl here. So dl is going to be, make a circle, right here, make it like that, get rid of that, oh. Maybe a little bit smaller. No, now I have to make it bigger. I just stuck with my instincts. I'm gonna say it like that. There we go. Bam. So this is the circle that we're going to use for the definition of V equals negative integral E dot dl for the electric field created by the electric field that creates the magnetic field. So, or maybe a better way to say it would be the electric field that is implied by the magnetic field. So since this is all radially symmetrical, this is going to be negative E integral dl, where dl is a small section of the circle. So integral.dl is really just going to be the circumference. So this is going to be negative E times 2 pi, I think R1, is that what they called it? 2 pi R1. Bam. So this guy's an area, pi R squared. This guy's a circumference, 2 pi R. Okay? And so this is voltage up here, this is voltage down here. So I'm going to say equals negative 2 pi R1. Now they want us to find the force. So the force is, what we're looking for is this E right there, that guy. So what I'm going to do is I'm going to say E equals 12t squared minus 2t all over, no, times pi r squared I don't like that t. That t is not much better. Worst t ever. Over 2 pi r. 1. There's probably supposed to be a negative in there. Oop. Okay. So this is going to be electric field. And then to find the force, we're just going to multiply by Q. So I'm going to calculate this guy out real quick. So let's throw in some numbers. So we have 12. Let's see, I think we have 2 seconds. At 2 seconds, t equals 2. So we're going to have 12 times 2 squared minus 2 times 2 quantities pi, and then r is what, 5? 3. So times 3 times 10 to the negative second squared over 2 pi, and we have R1, which is 6 centimeters. This would be 6 times 10 to the negative second. Okay, we can probably do some simplifying here. So 12 times 4 is 48. 48 minus 4 is 44. So we'll do 44. Then we're going to have 3 squared, which is 9. And we're going to have a pi. And we're going to have a 10 to the negative 4th. Okay? And then at the bottom, we're going to have a 2 pi. And then a 6. And then we're going to have 10 to the negative second. So one of these guys will cancel with one of these guys. We'll have a negative 2. The pi will cancel with the pi. The 2 will cancel with the 44. This will become 22. And then I'll just leave the 6 down there because I could... there's no sense making that like 3 halves. Or is there? I will. So then this becomes 66. 66. 66 divided by 2 becomes 33. Okay. So this is 33 times 10 to the negative second. Bam! I did that all in my head. By on the head, I mean on a piece of paper. But you know, I didn't even use Wolfram. Good for me. Good for me. And that is the electric field. It's supposed to be negative. Okay. Okay? So calculate the magnitude of the force exerted on the electron. This is going to be a small force. So I'm going to use force equals E times Q, which is, I'm going to do electron. It's like 1.6 times 10 to the negative 19th. Symbol, interactions, discovered, mass, electric charge. 1.6 times 10 to the negative 19th equals 1.6 times 10 to the negative 19th times 33 times 10 to the negative second. 33. I'm just going to call it 0.33. Basically divided by 3. So this would be like 0.53 times 10 to the negative 19th. So I'm going to actually Wolfram this guy. 1.6 times 10 to the negative 19th times 0.33. And I'm going to have 5.28 times 10 to the negative 20th equals, I'm going to call it 5.28 times 10 to the negative 20th newtons. And there was 2 negatives in there. There's a negative for this guy and there's a negative for that guy. I just canceled them out. Alright. That's small. Yeah, I guess that seems reasonable. So this would probably be like 5.28, and I think we'd probably just use E negative 20. Bam. Where that E is the times 10 to the such and such. Okay. So then the next question is, now looking through that, you're probably like, wow, this guy actually has no clue what he's doing. It's probably actually mostly true. I'm just familiar enough with the equations, and I'm like, well, maybe this equation will work. Maybe I'll throw that in there. And it's like I take a box and I throw in a whole bunch of the equations that I know, because there's only so many fundamental equations. Take the box, you shake it up, you look at it, you see if, oh, yeah, this is what I want. Or no, it's not. If it's not what you want, you shake it up some more until you get what you want. Not necessarily a good parenting technique, but it works well with a lot of physics problems. So that's basically how I did this. It's like, okay, we have, the force equals EQ, QV cross B equation. We know Lenz's law because we have a change in magnetic field with respect to time. Lenz's law gives us a voltage. We know the relation between voltage, electric potential difference, as I like to call it, and an electric field. And so I just followed the math, minimized actual understanding. And I got a number that's small, which seems, electrons are small, so it makes sense that you wouldn't need a whole lot of newtons on them. Yeah. Alright, so when T equals 2.0 seconds, calculate the direction of the force exerted on an electron located at point P1. Which is that distance? 6 centimeters. Okay, so they're asking the same. Now they're just asking, for first one was magnitude, now is direction. So the way I'm going to do this is I'm going to look here. I'm going to say, all right, over here for the electric field we had a negative. All right, so right here we have voltage, EMF. We have negative dB dt times A. So dB dt at 2 seconds is positive because we got like 44. When we plugged in 2 seconds, and then the area is positive, so we're going to have a negative. What that negative means is, so negative EMF. So that means that negative is going to oppose the direction of the B field we have here. So where you're going to create a magnetic, it's basically going to create a current, i.e. moving electrons, sort of. Moving electrons are going to, it's going to create a current that opposes this magnetic field. So using the right-hand rule, this magnetic field would be caused by a current going this direction, so down this way. So if we want to create a magnetic field coming towards us, we're going to want the current, let's do a different color here so we can, is that orange? So we want a current going this direction. Well, current is positive charges moving in the positive direction. Or the way it really works is negative charges moving in the negative direction. So if we have a current going that way, we're going to have electrons moving this way. So to create an opposing magnetic field, and we know it's going to be opposing based on our negative dB dt times area, Lenz's law equation. So the magnetic field that's currently existing is going this direction, so it wants to create a current going this way. To oppose it, we want an electric field, or a current going this direction, and a current going this direction to create a magnetic field coming out of the board. So this is how we got the first current. So we want the current to go that direction, which means the electron, which we're talking about right now, has to go down. So I'm going to say tangent to the electric field line passing clockwise. I'm going to go clockwise. So if you get two guesses on this, guess one direction, then guess the other direction. So I'm pretty sure the magnitude is 0 will be wrong. So that is how I do the first two parts. All right. So at what instance in this force is this force equal to 0? Okay, so the force is going to be equal to 0 when the electric field is equal to 0. And if we look at the electric field, right up here, this is our dB dt. So when this dB dt equals 0, then this whole top of the equation will equal 0, which means the electric field will equal 0. So when dB dt equals 0, electric field will equal 0. So what I'm going to do then, we know what dB dt is. Bam, copy and paste. Go down here, bam, right there. So this is what we already have for dBt. I'm going to simplify this guy. 12t squared, 12t minus 2 equals 0. Therefore I'm going to say t equals 0, or 12t equals 2. 2 equals 2 divided by 12, t equals 1/6. So at what instant is this force equal to 0? Consider the time after t equals 0. Oh, okay, so they're basically saying ignore the first one. So what is 1 divided by 6? It's like 1.166? Maybe? 0.166. So this would be 0.1667. So for this guy, you just take the derivative, set it equal to 0. 0.1667. And that is how this problem's done. Now I understand, like, my actual conceptual understanding of this is where this works in life for this one is pretty minimal. For this guy, I basically just throw equations at it until I force it into submission. So, long story short, came up with this problem, no idea what to do. I saw a B field with T's involved. I'm like, we're probably going to use Lenz's law. We're probably going to do dB dt. We're going to have some electromagnetic force. Threw in the equation, walked through that. I was like, okay, so now I have a voltage. How do I convert a voltage into electric field? I reached back like 3 or 4 weeks ago, a while, and I remember that V equals negative integral E dot dl. Bam, I think I used R in that when I do these videos. It doesn't matter. But that's talking about the circumference of the circle. I plug all those things in, I plug it in, and I get to use my one equation I use for all of my forces involving electric charges, EQ plus QV cross B. And I find an electric field, the implied electric field from the magnetic field, plug it in, and I get an answer. That's how I did it. That's how life goes. And then for the final, when things equal 0, voltage equals 0, or electromagnetic force equals 0 when dB dt, change in magnetic field with respect to time, is equal to 0. Bam! Got it? Alright, so that's it for week 8. See you later for week 9. If these videos helped you, they made your life a lot easier, make sure to subscribe, click the like down below. Thank you much. Take care.